Welcome to Calculus Notes 2.1, the derivative and the tangent line problem. So today we are going to be looking at our very first real problems in calculus. And we're going to develop this using the tangent line problem. So just a little review. The tangent line to a curve at a given point is the straight line that just touches the curve at that point. Now obviously that's not a very mathematical definition, but let's draw some tangent lines so that we can get an idea of what this is. So we want to draw a line tangent to the function at each of the given points. So we can use a ruler here to kind of help us do this. So we're going to put our ruler so that it just touches the line at only that one point and not at any extras. So you can see if I go too far here, I'm going to be intersecting in 2 points. And I want it just at 1 point. Okay, so that would be a possible tangent line there. If I try this one here, you can see there that I'm just going through that one and only point. Now you'll notice here with this tangent line that it actually intersects the point once here, and there's actually an intersection right here. But the way this works is we want the line tangent to the function at a given point. So this is the tangent line at this point because it just touches here, even though it may intersect the graph in another place. Alright, so let's try our next one. So we're getting it so it just touches that point. Now you notice you're going to kind of have to estimate where this slope is. This one's quite a bit steeper. And this last one looks like it's right about here. Okay. Now at Wikipedia they actually have the same graph and they show the tangent lines going on the entire surface. Let me show you that now. So here you can see the tangent line at each of these points. Now as we watch this again, notice the green here means the slope is positive. And when it goes to black, the slope is actually 0. Red is going to have a negative slope. Switches to black and then to green. Okay, so those are tangent lines at a point. So really, to define a line, you need a point, which we have here, and a slope. If you have those two things, a point and a slope, then you can define what the line is. So we're going to talk about this now. The problem of finding the tangent line at a point P boils down to the problem of finding the slope of the tangent line at point P, because then you'll have a point and a slope. You can approximate the slope using a secant line through the point of tangency and a second point on the curve. So we've already talked about these secant lines a little bit before, but let's just review this. So let's go ahead and draw a curve. And this is our curve f of x. And we're going to give it an x value here of c, and we're going to put a point right there. So what is the height of this point? If we come over here, this is going to be f of c. So if we want to be able to find this tangent line, okay, which looks to be about right there, what we're actually going to do is draw a secant line, something like that. So a secant line actually crosses at 2 points on the graph. And this is going to be an approximation for that tangent line. So when we look at this other point, we say that it is delta x units away. And remember, delta x is just the change in x. So this becomes the x value of c plus delta x. So we've already come c units, and we go an extra delta x units. So this is the x value of c plus delta x. Now if we think about this distance right here, okay, we would map this point. What's the height of the graph right here? Well, it's our function where x is c plus delta x. So right over here, this is f of c plus delta x. So if we're going to find the height here, or so if we're going to find this height, or the rise in our function, if we look at these two values, this is actually going to be this y value minus this y value. And so this is really f of c plus delta x minus f of c. So just for review, slope m, remember, is the change in y over the change in x, also rise over run. And based on our drawing here from this point to this point, so by looking at the graph, the change in y is right here. So we're just going to write that as the f, the function of c plus delta x minus f of c over the change in x, which is just delta x. And you might recognize this as being the difference quotient. And we're going to learn about how the difference quotient can help us to find the tangent line, which would have been somewhere about there. Okay, so to do this, we're going to make closer and closer approximations, okay, of increasing accuracy of the tangent line to the function by letting delta x go to 0. So that's our trick there. We're going to let this distance get smaller and smaller until it goes to 0, and then that's going to give us the tangent line. So what we can do is start off with a secant that's fairly far away. We can go through those 2 points, and here would be our delta x. And make it large because that's a pretty large delta x. Now if I want to make increasing accuracy, I'm going to move this secant line, I'm going to move this point closer now to my c. So notice my delta x is getting smaller. So I want to move the point even closer now. Let's go right there. Now you can see delta x even smaller. And what we're doing then is letting delta x go to 0. Now obviously if we just draw it at 0, it may not exist there because we don't have the 2 points to draw our line through. But by getting closer and closer, we're becoming much more accurate. So here you can see delta x is tiny. going to 0. Okay, so let's talk about the definition now of a tangent line with a certain slope. So if f is defined in an open interval containing c, basically saying the function works on an interval, and if the limit as delta x goes to 0 of the change in y over the change in x equals the limit as delta x goes to 0 of f of c plus delta x minus f of c over delta x, and that equals m, if that exists, then the line passing through the point c f of c with the slope of m is the tangent line to the graph of f at the point c f of c. So basically what it's saying is, if we can take that limit of the slope of the secant line as x goes to 0, that's going to be the slope of our tangent line at that given point. So remember, all we needed was a slope and a point. So if we can achieve those two things, we can find what the tangent line is. Now, one other note, very important, is the slope of the tangent line is also called the slope of the graph at a point. So you can see here we have many slopes happening, but if we can find the tangent line, it's the same as the slope of the graph. So here it says, find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at the point -1, 2. So here's our point, -1, 2. And our tangent line is going to be somewhere right in here. So let's go ahead and find the slope of this tangent line. So let's use our definition right up here. And to do this, all we need to find is c. So c here equals -1, because it comes from the point we're looking for. Okay, so here is our c. So we're going to substitute now c into this equation. So we have the limit as delta x approaches 0 of f of c, which is -1, plus delta x minus f of c, which is f of -1, over delta x. So our first step was to substitute c. Now to find this limit, why can't we just use direct substitution? Well, if you see, we could put 0 in down here, and that would give us our error. So we can't just use direct substitution. So we are going to have to find this as we go. Now it gets a little tedious, but every time I do want you to rewrite the limit as delta x goes to 0, because it keeps reminding us what we're trying to find. Now anytime you see f, what I want you to do is open up kind of square brackets right there. And what you're going to do is you're going to replace -1 plus delta x in for x in our function. So anytime you see x, you're going to put -1 plus delta x. So we have -1 plus delta x squared plus 1. And then you're going to close your square brackets. Now we have minus. So we have minus. And now you see another f, so you're going to open up your square brackets. And now you're going to do f of -1. So you're going to take -1 and substitute it in for x in our function. And remember, we're going to use parentheses here. And then you're going to close off your square brackets. And this is all going to be over delta x. So what we did here is we went ahead and subbed everything into our f function. All right, from here on out, now we're just going to simplify everything because now we're down to just numbers and delta x's, which is what we wanted. So we do want the limit as delta x goes to 0. So we have negative 1 plus delta x squared, which is 1 minus 2 delta x plus delta x squared, then plus 1. And that's it for this red brackets. And we still have minus. Then in these red brackets, we're going to get negative 1 squared is 1, plus 1 is 2. This is all going to be over delta x. And this is always how it's going to be. With your left part, you're always going to have delta x's still in here. With your right part, since c was just a number, you're always going to get a number here. Now something very interesting happens here. When you look at this, we have a 1 and a 1, which makes our 2, and then we're going to subtract a 2. So those essentially cancel out, and we're left with negative 2 delta x plus delta x squared. And all of the constants dropped out. And we still have divided by delta x. And we still have the limit. Okay, so at this point, what we did here was simplify. Now if we look at this, remember the problem with direct substitution was we couldn't put 0 in for delta x, but now watch what happens. We saw the limit of delta x goes to 0. We can factor a delta x out of the numerator. So we still take out a delta x out of this factor, and we take a delta x out of this. And there we have our factored form. And now if you look at this, the delta x's here are going to cancel. So in this step, you want to cancel your delta x factor. So what we're left with now is a limit that we can solve using direct substitution. So the limit as delta x goes to 0 of negative 2 plus delta x. So we just have a polynomial function. We're going to use direct substitution, so we get negative 2 plus 0, and this equals negative 2. Okay, so once you've factored, canceled out your factor, here you want to use direct substitution. All right, so you definitely want to look at these here. You've got to substitute in your c. You're going to sub everything into your functions, f. Then you're going to simplify everything, so actually working out some of this. Then you're going to factor out a delta x and cancel it, and then you're going to use direct substitution. So what is this telling me? This negative 2 tells me that the slope of my tangent line has to equal negative 2. So if I know that this is the point, negative 1, 2, the slope is going to tell me to go down 2 and over 1. So down 2 to the right 1, and now I can draw my tangent line. So you can see the definition of the tangent line is the slope with the point combined, and then we're good to go. Now, if we wanted to find an equation for this tangent line, we would say that our slope is negative 2, and the point we're using is negative 1, 2. And so we're just going to use point-slope form, like we did in our first chapter. So we have y minus a y value, so we'll pick 2 there, and then equals m times x minus our x value, which is negative 1. And then we would just simplify this. Let's see, 2 negatives make a positive. So it's negative 2 times positive 1, which is negative 2. And we're going to add 2 to the other side. We get y equals negative 2x. So this process shows how to find the slope, use the slope and the point to find the equation of the tangent line. Now what's also true of the graph of f of x at this point is that the slope is negative 2. So at this point we know our slope is decreasing by negative 2. Alright, let's move on to our next example. Now our next example is very similar, but it has a little bit different question. It says find the slope of the graph of f of x equals 2 minus 3x squared, so we still have a function, at any point c, comma, f of c. So now they don't tell you what point we're using. Let's go ahead and draw the graph of this so that we can kind of visualize what's going on. So we get 2 minus 3x squared. So we know it's going to intersect at 0, 2. And then as we move 1 to the right and left, it goes down 3. So it's kind of a steep looking graph there. And what we're trying to do now is find the slope of this at any point along this function, whether it be here or anywhere. So what we're going to do here is we're going to start with our limit definition of slope. So we're going to do the limit delta x goes to 0. We're just going to rewrite our difference quotient here. All right, and that needs to be memorized. Now, we don't have a c to substitute in there, so we're going to jump straight to plugging this into f of x. Okay, so remember the square brackets. And here's f of c plus delta x. And here's just f of c. All right, so once we've substituted into our function, we're going to actually simplify this. So here we have 2 minus 3 times this binomial squared. So you remember it's the square of the first term plus 2 times both terms. So 2c delta x plus the square of the second term. And that 3 is going to multiply all the way across here. And then we're going to have minus. Well, there's really nothing else we can do with this, so let's just apply the negation. So minus 2 plus 3c squared. Over delta x. All right, so now we just have to keep simplifying. This is just all Algebra 2 work here. So we're going to distribute the negative 3. Remember to tag on your limit. Well, one thing you can notice here is that this 2 and this negative 2 are going to cancel. So we can cancel that out. We don't have to even write the 2 there. Let's just distribute the negative 3. So negative 3c squared minus 6c delta x minus 3 delta x squared. And then we still have plus 3c squared over delta x. Now I told you before that all the constants were going to cancel out. Is that the case here? Well, here we have negative 3c squared, and c, remember, is just any number, and here we have positive 3c squared. So these two parts are going to cancel out, and those are our constants. And you can see that all we're left with are terms including a delta x. So we move on to factor out that delta x. And here at the beginning, it's a good idea to show that factorization. So if we take a delta x out here, we're just left with negative 6c. If we take a delta x out of delta x squared, we're just left with delta x. And now you can see that these delta x's right here are going to cancel. And now, since delta x is no longer in the denominator, we can use direct substitution. We're just going to plug 0 in for delta x. And we're left with negative 6c. And that is the slope of a tangent line at any point c, f of c. Becomes an equation. So let's go ahead and just see. What if we went where c equals 1, which is right here? What would be the slope of the tangent line? Well, we know that our slope equals negative 6c, so we're just going to substitute that in. So it's negative 6 times 1, which is negative 6. So we can actually put another point here to get our tangent line. So negative 6, 2, 3, 4, 5, 6, and then over 1. So this would, in a sense, give us the slope of negative 6, so we can draw that. Okay, and so there would be our tangent line. What happens if c equals 0? What is your slope? Well, m equals negative 6 times 0, and it equals 0. So you can see that would be a horizontal line right here. So the slope of this tangent line at 0 would be 0. What if c equals negative 1? What would your slope be? Well, m equals negative 6 times negative 1, which would be positive 6. So here we'd go up 6 to the right 1. And there we go. So you can see that finding the slope for any point c f of c helps us to quickly find the slope at any point because we know the equation for the slope. Now just one note that this will not work where the graph is vertical. because the limit that you get is going to be infinity or negative infinity, which doesn't exist. So you just have to be careful. It's not going to work where we have a vertical graph. Okay. So that might be a graph that kind of looks like this one. So right here, if we have a vertical line, it's not going to give us a slope because we know vertical lines have undefined slope.